Hello, I'm Peter Batty with SSP Innovations. I'm going to talk to you today about eliminating the as-built update backlog using automated field data capture. So this is a quick overview of what I'll talk to you about. First, I'll just explain the as-built update challenge briefly for anyone who might not be familiar with it. And really this is equally applicable to underground and above ground assets, and a lot of what I'll talk about will be applicable to both, but then I'll zoom in a little bit on a few things that are specific to underground. I'll talk a bit about technology enablers that can help us address this challenge, show you a couple of demos of some work that we've been doing to develop solutions in this area, and I'll talk a little bit specifically about some aspects of location accuracy that I think are of interest for underground in particular, although again for both. And then a little bit of time for questions at the end if we have enough time left. So basically the as-built update backlog, for anyone who's not familiar with it, is the time from installing something in the field, a piece of equipment, to getting a record of that back in your GIS or other back-end systems. And in utilities and telecom companies today, this is generally measured in months. You can see some statistics here, which is pretty shocking really today when we have real-time aspects of, or real-time data about so many aspects of the real world, from traffic to weather to the location of our phones and much more. So you know, it's not a good state of affairs right now. So it's worth a quick look at why is this such a big problem? And really the root cause is that geospatial data capture is too complex and time consuming for the people who construct and install equipment in the field. And you know, there have been a lot of efforts to develop mobile apps. I've spent a lot of time on that myself. But still, even with apps that are quite easy to use and simple with today's approaches, they still tend to be too complex for the people who are actually doing construction and too time consuming. And so the bottom line is, even though in some cases there might be some successful examples of capturing simple data in the field, overall, in the great majority of cases, the as-built update process requires someone else to come along and capture that data, someone with more training, more specialist knowledge. And as soon as you do that, the whole process, as soon as you bring someone else in the loop, the whole process becomes inherently resource intensive, costly, and has this built-in delay. So really the key to solving this problem, in my mind, is to enable crowdsourcing of updates from the people who actually do the construction, the field workers. So sometimes we like to call that field sourcing. So they can just make those updates where and when the work happens. And in order to do that, we really need something that is much faster and simpler, which basically means more automated than today's solutions. So let's look briefly. The good news is that there are a number of enabling technologies that can really change the way that we approach this problem, and I list them on this slide here. So things like computer vision, machine learning, augmented reality, voice interaction, and reality capture can all play a role. A lot of these things are being driven by other industries outside the geospatial technology industry, which is sort of an interesting aspect of them. So I think part of the challenge in bringing together a solution is looking broadly at these different types of technologies and where they're applied, and bringing them together into a solution for utilities. I'll just show you a few quick examples. So this is an example from Tesla of their self-driving car software. And you can see here it's recognizing spatial objects like stop signals, traffic lights, cars in real time, multiple times a second. And obviously that has a lot of parallels with recognizing assets in a utility or telecom environment, including underground assets while they're exposed during construction. Image recognition is another thing that's very pervasive in lots of different applications, a lot of consumer applications, everything from tagging people in Facebook to tagging subjects in photos, whether it's Amazon Photos or Google Photos or other services. And those kind of recognition services can be easily trained now, and so they can be very applicable to capturing geospatial data automatically too. Then augmented reality is being driven by a lot of different industries. Pokemon Go is a huge success, which is developed by Niantic, the original developers of Google Maps, and there's a lot of mapping elements in that. And then in a more localized environment, IKEA is doing interesting things, just one of many companies, but an example of a sort of mainstream company using augmented reality for interior design. And so it's really being used for a lot of current production applications in different areas. Let's just watch a quick video on something called the AR cloud.
Our physical reality is changing. The internet is moving off screens and out into the world around us. Digital information, content, and shared experiences will blend into view, impacting every aspect of our lives, culture, and economy. This feature is made possible by AR cloud technology, which includes machine-readable maps that tech giants and startups are currently spending billions of dollars to create. To reach it.
So I just wanted to pick up on that last point there, where they said, which includes machine-readable maps that tech giants and startups are currently spending billions of dollars to create. And this is going to be a huge development for the geospatial industry in general, and applies to this whole area of improving underground data quality. Basically, people are building very, very high resolution, high accuracy point clouds and sort of 3D image-based models of the world. A lot of it driven by the desire to do augmented reality applications. And I'll explain a bit more about that as we go through the presentation, but that's a very exciting development. And these are some of the main players working on this area and related areas, and I won't go into details of them in the interest of time right now. I just wanted to offer a couple of thoughts on AR for asset records. I think that to some degree AR for asset visualization has been somewhat oversold up to this point. I'm sure we've all seen cool demos of pipes being displayed under streets, and that concept is absolutely valid. But there's a couple of challenges in the real world. One is that AR technology really isn't fully there yet in terms of the ability to accurately position data that has a latitude, longitude in a GIS database in the real world. It tends to be too far off for a lot of use cases, but that is going to improve with this concept of the AR cloud very shortly. And then the other thing is that the underlying GIS data quality just isn't good enough in most cases, which obviously is one of the main topics of this conference. How do we improve that? But when you combine those two things, I think it's not quite there for visualization yet. Like I said, the AR cloud will help with that, and I'll give some examples of how that's already in progress. But to me, AI is much more useful for data capture today, for the sort of applications that I'll show you shortly, where we're starting with the real world and adding things in there, and it's just much easier to synchronize the real and virtual worlds in that particular scenario, as you'll see. So with that sort of background, what I'd like to do now is show you a demo of the SS Vision product, which is a new product we've just announced that I've been leading for the last year or so, and we're very excited about how this can impact mobile data capture to reduce the as-built updates backlog, as I've been talking about. So let's watch the first demo. We're at a new subdivision construction site here, and we're going to do some as-built data capture of some electric equipment using an iPad. We point the device at an electric pedestal, and the application displays at the top of the screen what it is, and the user just taps the screen to add a feature. Next we point at the neighbouring electric meter, and again it's automatically recognised and we tap to confirm that we want to add it. Then we scan the meter to add more detailed attributes according to rules that we've set up. Now we'll add the path of a cable. If the trench was still open so the cable was visible, we could automatically recognise it, like we did with the other features, but since it's hidden we select it from a list and then just tap to add points along the path of the cable. As we walk you can see the cumulative distance of the cable path being shown at the top. Lastly, we'll add this electric cabinet in the same way and scan attributes in several different locations, including the transformer number and manufacturer on the front side, then the kVA from that yellow 50 on the side, and then we zoom in more closely to get additional attributes like the serial number and work order number from the smaller label. Then the data gets pushed automatically to the GIS with no user intervention needed. We can see the features that we just captured here on the map with their attributes plus photos. The data is immediately available in any GIS client. We're looking at it in ArcGIS field maps on the iPad here. We could similarly see it in our SSP MIMS or 3GIS mobile products. Here we see the same data in field maps on the iPhone, just with a slightly different form factor. And the data can be viewed in any web browser too. And the data can then be pushed on from the GIS to real-time systems like an ADMS, outage management system, or network management system. Okay, so we covered quite a few things there, and I just wanted to give you a quick summary of some of the key technical elements there. So basically the app is able to automatically recognize features and attributes using the list of things you see here, machine learning based image recognition to tell what type of feature it is, reading barcodes, QR codes, and doing text recognition to capture detailed attributes, and also to reinforce the feature recognition in some cases. And then you can also use voice recognition as a backup if there's a scenario where you have to correct something that was misrecognized or something can't be read correctly. And then we use augmented reality, and in this context it has several benefits. I think it's more intuitive to display the captured data on top of the real world rather than having to do with this mental translation between a 2D map and the real world. It adds much greater relative accuracy, and I'll show you examples of that shortly, including distance measurements. And then it also captures data in 3D, which is especially useful for underground assets. So if we're capturing underground assets while they're exposed during construction, then we can not just calculate the X and Y, but we can calculate the depth below ground level as well. So let me give you one more demo just with a few more miscellaneous examples to give you a flavour for what else you can do. Here we're going to capture this row of gas meters. We've set up the rules to just capture the meter number, which can be read from the text label or the barcode. We could scan additional attributes if we wanted to, but that wasn't needed in this case. The augmented reality really comes into its own here, as its high relative accuracy lets us record the order of these meters and the distance between them, which is something we couldn't do with GPS alone. You can see how well the augmented reality data fits to the real world as we scan back along the row of meters here. We can also use voice recognition in scenarios where an attribute can't be easily read with text recognition. 34758. As with text recognition, we intelligently work out which attribute to store this value in, transformer number in this case. Lastly, here's an example of capturing very detailed attributes from an electric meter. We capture 22 attributes in just over a second here. And then we also show that if needed, you can display all the captured attributes in a traditional form, where we can update values by voice recognition, selection from lists, or as a last resort by typing. We expect this to hardly ever be used based on the accuracy of text recognition in our testing so far. Okay, so hopefully you can see that Vision really is much simpler to use, much faster to capture data than traditional field data capture applications. And like I said, it's really equally applicable to underground and above ground assets. In general, those demos were primarily above ground assets just because doing our testing, obviously it's easier to access those, whereas underground assets we need to capture during the construction phase while they're still exposed. I also just wanted to briefly mention that while I've really focused on as-built updates here, this is applicable in multiple business scenarios, and I'm not going to go through all of these, but the other one I wanted to mention is just data validation and correction. Again, obviously existing data quality in a lot of cases has issues, and so you can use this same technology just while people are doing their normal work in the field and accessing assets to verify that the existing records match what's actually in the field and make updates where appropriate. And again, this is easier with above ground assets in that you can always see them, but you can apply that same principle to underground assets whenever you're doing construction work and you might uncover some existing assets, then you can verify their details and location using this kind of application to check the quality. So I just wanted to talk about a few things relating to location accuracy, because I think this is particularly important for underground assets more so than above ground assets, that the requirements are typically higher. So just briefly to reiterate, in this use case with field sourcing, it's really important that anyone can use the system with minimal or no training. It needs to take them minimal time, and it needs to use, on the whole, inexpensive commodity equipment. If you've got hundreds or thousands of field workers, you can't give them all specialised surveying equipment. So higher precision GPS on the whole will be too expensive and too complex for this particular scenario and user base, although there could be places for its use in specific circumstances. So the interesting thing here is that AR gives much greater relative accuracy than consumer GPS in phones does. So it measures accurate distances and angles in 3D, as I mentioned, for recording of relative asset layout. And in my testing, I found that distance measurements on the whole, in the range of tests I've done, is accurate to more or less 1%, I've found. So here's just a simple example I just did at home here to measure a 10-foot distance next to a tape measure here. I've added a virtual pipe, and you can see the measured distance in the Augmented Reality app is 10 inches, and it's within an inch of the 10-foot mark on the tape measure there, and then that distance is showing to 1 decimal place, so it's within sort of 1.12 inches. So we're within pretty much 1% here. And I've done tests up to about 100 feet where I've found that same sort of accuracy of being within 1%. So much better than you could get with anything except the very highest precision GPS. Certainly you couldn't get close to that with consumer GPS in a phone. And so here's an example of how we're applying that concept, that the way we actually calculate coordinates with what we're doing there is we use GPS offsets from a single base GPS coordinate. So in the left-hand picture here, you see I was capturing coordinates at the corner of this basketball court, so it's not a utility app, but it was a nice convenient way of just doing some quick testing on accuracy. And you can see the offsets here aren't very consistent, especially if we look at the pairs of points in the middle, which should be on the corners of the courts and the end of the halfway line. The offsets are sort of irregular there, whereas if you look at the points on the right-hand side, which is using the augmented reality technology, the orientation is much more consistent, and the distance between them, in the middle there's a sort of origin point, you can ignore that, but the two outer points are the relevant points. And then the offset from all of the points captured is much more consistent. They're all in the same direction and more or less the same distance. So you get a much better, more accurate picture of the shape of the basketball court in this particular case. So just to explain a little bit more, what we're doing on the right is that, like I said, we're capturing a single base GPS coordinate for the whole area that we're capturing. And there we just pick one of the more accurate GPS coordinates that we have captured based on the sort of estimated accuracy that you get back from the GPS receiver. And then all of the rest of the coordinates, we add the offsets in the augmented reality space, which I say has this very good relative accuracy. So you really get the shape of things much better, and that can be very good if you're trying to capture network connectivity and so on. And then it's also worth saying that in a particular scenario, if you really wanted higher base accuracy, because just to reiterate, we're not getting higher global accuracy on the right-hand side. It's subject to the same errors that any individual GPS reading on the left-hand side, but we're just getting the better relative accuracy. But you could use a high-precision GPS, and then that would improve the absolute accuracy of all of these coordinates in a similar way. It's also worth mentioning that if you're capturing an asset that already exists, then you could easily translate the data that comes back to match that existing asset in the database, which you might well want to do anyway, so that's another way of refining the accuracy. But anyway, it does, augmented reality does help with that aspect, which could be very useful. For example, you could also capture data on like a curb or the location of a manhole or a building corner, and then sort of record the relative information to the location of a pipe or an underground valve or whatever it might be. So quite a bit of potential with the augmented reality stuff there. Oh yes, I also just wanted to mention that this is the way that I walked around the court here. So I walked around the left-hand court first and captured all of the points on the left-hand side. Then I walked around the right-hand court So those the bottom pair of points and the central pair of points weren't captured immediately after one another. I'd walked all the way around the court. So again, that just reiterates how well the augmented reality holds its position. And then a second example I wanted to mention is a second technique we can use rather than this GPS base plus the hour offsets is to use what Apple calls GeoAnchors. And this is their implementation of the AR cloud. And so basically the idea there is that you can, it uses GPS for a course location on the phone, but then as you're moving the device around, it uses the camera view to match what the camera is seeing against highly accurate street view type imagery, which Apple calls look around imagery, and that refines the position. And I haven't done really rigorous testing of this. Ultimately I want to do much more detailed testing against high precision GPS coordinates and do some real sort of statistical calculations. But just from a number of quick tests like this one, I've been really impressed with the results. So here I placed points at the two corners on the east side of the pedestrian crossing there and at the corner of the grass. And just estimating from looking at this imagery, they're both within a foot or so of the position on the imagery. So much, much better than what we typically get from GPS only. And in general, I've had pretty consistent results doing similar kind of ad hoc tests. So this really looks very promising, and I think this is this type of system, which a lot of people call a visual positioning system, it is really going to become to supersede GPS in many cases, I think, because of its accuracy and the ability to just run on a standard phone. And I just wanted to mention briefly that these are the cities it's available in, that Apple's particular service here. It's available in 22 cities in the US today, including Denver, where I'm based. And they plan to expand that pretty rapidly. It's pretty heavily based on their street view type imagery, or look around imagery as they call it, and that has a longer list of cities and quite a lot more non-US locations. So you can probably expect it to come to these locations relatively soon. So that's a little bit about accuracy. So I think there's a number of interesting things about the use of augmented reality for improved accuracy, in particular for underground. I also just wanted to mention that our long-term vision for this approach is to really be able to support full automation. So what you saw in those demonstrations today, it's fairly largely automated, but there's a number of simple user interactions. But over time, we feel that we'll be able to transition to either a helmet-mounted phone or something that's kind of like a GoPro camera with a processor built into it that could be mounted on a helmet, and basically where you could run the whole thing without any user interaction. It would just watch what the user's doing, capture relevant data as you go through. So I think that's ultimately where this will end up. That will take a few years, but we can see really all the key elements that we need to do that. So that's another exciting aspect of this. So I just wanted to summarize, what I think are some of the important points that we talked about. I really feel that improving the as-built update process is crucial to maintaining accurate underground and above ground asset records. So I think in the conference here we've heard a lot about how to improve the kind of base state of the data, but it's really important to look at these ongoing changes, because even if you update all the records using ground penetrating radar or whatever, and get a much more accurate base set of data, the next day it's going to be out of date because you're changing the network every day and it's going to get more and more out of date. So addressing the as-built update problem is really key. Like I talked about, field sourcing of data is really key to me, that you need to enable the people doing the construction to capture the data. And these new technologies that we've talked about really open up some very exciting new ways that we can give systems to the construction workers to enable them to do that. Talked a little bit about visual positioning systems, and I think they're really very likely to supersede GPS in a lot of scenarios. Like I said, you can get very accurate data just from a smartphone. I think it's worth putting some thought into ways of storing relative positions or offsets in additional to global coordinates as we're capturing this type of information. Because with things like visual positioning systems, we may well have improved mechanisms for capturing the global coordinates over time, and if we know those original relationships that we use to capture data, we can just shift things in a more accurate way. So hopefully there were a few things of interest in there. I think it's a really exciting time in terms of possibilities for improving asset data quality right now. And with that, I'll wrap up, and I'll be happy to take questions if we have time for that. Thanks very much.
Peter, that was fantastic. Very interesting.
Oh, thank you.
First question is, in terms of your voice recognition software, is the system compatible with languages other than English?
Yes, it is. We're using primarily Apple technology in different aspects of the application. So we use Apple voice recognition, which can recognize most major languages, well, like quite a number of languages from around the world. So yes.
What certified training would technicians and operators in the field need for this technology?
Really, our aim is very minimal training. As I talked about in the presentation, we're really targeting non-technical field workers. That I feel that's the key for this as-built update scenario. Is you shouldn't require technical people with special training. So our intent is it's a few minutes of training via video or something like that, but really something that people can just pick up and use is our intent.
How would a civil engineer use this application for gradient measurements? Is it accurate enough?
Yeah, a good question. As I mentioned, and we're still at fairly early stages with this. The product's in development. We'll be releasing the first release quite shortly here. As I mentioned briefly, just from rough testing, I found that the distance measurement, doing some tests up to 100 feet, 30 meters or so, has been probably within 1% in both X, Y, and Z or Z, depending on which side of the border you're on. So, I think you can probably use that as a rough rule of thumb that you'll probably get distance measurements within 1%. So if that's good enough for your gradient measurements, then yes, I think.
How would you address the privacy? How would you address privacy with GoPro mounted on workers' helmets? Google Sidewalks Labs Quayside 1.0 ran into that problem in the city of Toronto.
Yeah, so I think, as I talked about, that's a sort of future thing to have the GoPros mounted there. In general, I think these kind of privacy issues are easier to manage in a sort of restricted or in a more specific work environment as opposed to in the social side of things. Google Glass ran into that problem, which was a sort of early attempt at kind of always on camera type things that in a social setting it's pretty weird. But I think if you're on a construction site, then I think it's a lot more manageable. So that's not a complete answer, but overall I think it's manageable, given the potential benefits here that the trade-off versus privacy concerns, I think is something that I'm not too concerned about.
Another question, where does the training data come from?
Yeah, so another good question. So, and for people who are not familiar with that, that's really referring to when you have a machine learning sort of computer vision based model like we're using there. You use machine learning and you have to give it images to train that. And so up to this point, we've just captured a number of our images ourselves. And so one of the things we see as we have more customers rolling out with this is that every time we capture an asset, we capture an image for that, and we can use that to feed into our machine learning models. So, we don't share customers' data, but we, at least our plan is in general to use those images to further train the model. So over time, that will get better and better. But I mean, one other quick comment on that is just that with the approach that we're taking, where the user confirms something and the user can override things, you don't need the same the same amount of imagery as you do if you're doing something that's 100% automated. Though, as I talked about, over time, and as we have better models, we'll move more towards full automation.
Fantastic. Well, we're in our break. Is there anything you would like to, closing thought you'd like to leave with the attendees before we head into that?
No, just to say thanks everyone for attending. And obviously, if you're interested in what I talked about, feel free to reach out to me. But, I do feel this is a very exciting area and that there's real potential for these technologies to offer some significant improvement in what we can do to really improve as-built updates out there.
Excellent. Peter, thank you so much for sharing this with us. It was very interesting. I know Jeff's been talking about it for a while and looking forward to your talk.
Great. Well, thanks very much for having me.